Okay, let's talk about the real number system. We talked about this, we have talked about this before in class, but I just wanted to have you have a sheet of paper that this is all listed on, because we're going to start to see questions about it in Fred, and I wanted you to be ready. So again, when we talked about this before, I said, consider this like those nesting boxes that you had when you were little, or the nesting cups that all kind of fit snugly into each other. That's kind of like what the real number system is, except for this spot over here, which is kind of the exception, and we'll talk about that. But the smallest set right here is called the natural numbers, and we abbreviate it with this kind of funky looking N. It's just a fat N that we put in there. So this is the natural numbers, and again, I'll draw an arrow here. The natural numbers. And this is numbers that represent things that we would see in nature. So 3 flowers, or 8 trees, or 10 puppies, or things like that. So really it's the set that contains the numbers 1, 2, 3, 4, and so forth. It is infinitely large, right? It just continues going on forever. Okay, the next larger set is only larger by one element. This set is called the whole numbers, and there is no shorthand notation for it or symbol. So it's just called the whole numbers. And just like in our nesting boxes, the whole numbers contain everything that was in all the smaller sets, plus the only additional member of this set is 0. All right? So it now ends up being the set that is, if I were to just write this in a set notation, 0, 1, 2, 3, 4, and so forth. So just the same as before with the natural numbers, except now we've just added 0 to that set to get the whole numbers. I remember when I was learning them, I was always confused about, well, which is which. You can think that whole sounds like the word H-O-L-E, whole, which is just kind of a void, which looks like a 0. So that's how I remembered that whole numbers contained the whole, which looks like 0, and natural numbers did not. Okay, the next set of numbers that would that would contain both the natural numbers and the whole numbers would be the integers. And if you were to guess what the symbol would be for this, you would never guess it. Actually, I told you in class what it was, but it is this fat Z. All right, and the reason that it is the fat Z is because it comes from the German word, I think Zahlen or Zollen or something, which means to count or numbers. And so that's where it came from, because the guy that invented that symbol was German. So the integers contains all the natural numbers, all the whole numbers, but now it's also going to contain the negative versions of that. So this is going to be -4, -3, -2, -1, 0, 1, 2, 3, and so forth. Infinitely large, but extending in both directions now, not just one. Okay, and then the next setup, things start to get really big here. All right, now we're going to start talking about the rational numbers. And again, the symbol for rational is not intuitive. It would be a giant Q. Q standing for quotient, all right, which should give you a hint as to what kind of numbers are in the rational numbers. It's anything that can be written as a fraction where the numerator and denominator are integers. All right, so let me write that down there. The rational numbers. It's the set of all numbers that can be written in the form A over B, where A and B are integers, and b is not equal to 0. All right, no zeros in our denominators. So it's any number that can be written in the form a over b, where a and b are integers and b is not equal to 0. That doesn't mean that they will be written in that form. It just means it can be written in that form. So there are some obvious things that we would put in here. Some of our nicer fraction friends, 1/2, 3/4, you know, something like 7/10, things like that. But then there are the decimal equivalents of these. So we could also write 0.5. We could write negative 0.75. We could write positive 0.7. So any of these fractional values could be written as their equivalent decimal values. Now, that would also mean things like, you know, that we don't even think of as nice fractions, like maybe 0.1234, because this is the same thing as 1,234 10,000ths. All right, it can be written as a fraction with an integer numerator and denominator. It doesn't mean that we normally do write it that way, but it can be written in that way. It would also be things like, and starts to weird people out maybe, 0.3 repeating. 0.3 repeating is the same thing as 1/3. Really anything that is a repeating decimal. 0.162 repeating is a fraction. It does have a fractional equivalent. If we had more time, I would teach you how to change this into its fractional equivalent, but I don't have time. So anyway, anything that repeats or ends. So we say the set of rational numbers, this is all, it's either written as a fraction or how about we say, can be written as a terminating, right? Terminating, think of exterminate. An exterminator is somebody that comes and ends all your bug problems. A terminal is at a train station. It's the end of the line, all right? So it's an ending. So terminating, or I think somebody brought up in class, terminal cancer. If you've ever heard of that, it is cancer that will end your life. So terminating talks about an end. So when we talk about a terminating decimal, it's a decimal that has an end. It does not go on forever. So things that are in this set, if they're not written as a fraction, they must be written as a terminating decimal or a repeating decimal. All right. So if they're not written in this form, a over b, where a and b are integers and b is not 0, then the other form that they could be in is a terminating or an ending decimal or a repeating decimal, which again means that it repeats the exact same pattern over and over forever. Now, I want to clarify this right here. If we were to write 0.1234567 ... that is not a repeating decimal. It has a nice pattern to it, but the pattern is not repeating. It's going 1, 2, 3, 4, 5, 6, 7. The next one would be 8, then 9, then 10, then 11. So we're not talking about something that just has a nice pattern to it. It has to have a pattern that repeats over and over, forever and ever. All right. So this, I think, is the set that causes most people the most trouble, just because there are different ways to think about that. Natural numbers, very nice. Whole numbers, very nice. Integers, very nice. But when we start to get to rational numbers, because there are different ways we can think of it, they become a little bit more difficult. And again, don't forget that rational numbers contain the integers, because all integers, like -4, could be written as -4 over 1. Or you could think of it as a terminating decimal as -4.0 or something. It also contains the whole numbers. All right, 0 is a rational number because it's 0 over 1. It also contains a natural number, so, you know, like 7 is 7 over 1. So all of these sets are also included in it. The rationals is a huge, huge set. Remember I said that this set was infinite. This has one more in it, so it's also infinite. This is infinite. These three are infinite, but the rationals is an even bigger infinite than these. Again, mathematicians have gone crazy talking about different degrees of infinity. This one's a mind blower right there, that this set of numbers is an even bigger amount of infinite than these. Okay, so then we've got this one little strip here reserved. It's little only because we don't have much space here, but not because the set is little. If this part made up the rational numbers, this is the irrational. Right? It does not have its own symbol. We just say irrational numbers. The most famous member of this set is pi. All right. An irrational number is something that's not rational. So we're looking at things, at decimals that don't terminate or decimals that don't repeat. So this example that I gave to you of 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that one right there, that would be irrational because it does not end and it doesn't repeat. There is another number that has a symbol. It's called E. You won't learn about that until you get to calculus, but that is another famous irrational number. Lots and lots of other famous irrational numbers. Square root of 3. All right, what number times itself equals 3? No nice number. If you plug that into your calculator, let me see if, here's my calculator right here. If I plug that into my calculator, I get that it is approximately equal to 1.73205080, and it keeps going, right? It does not ever end. So any number that doesn't have a perfect square would be in here. Square root of 2, square root of 3, square root of 4, no. Square root of 4 would end up actually in the whole numbers or even the natural numbers because square root of 4 is just 2. So no to square root of 4, yes to square root of 5, square root of 6, square root of 7, square root of 8, no to square root of 9. That's, again, in natural whole numbers, integers. So anything that's not a perfect square would end up in this. We also will learn about things called cube roots. What number times itself 3 times gives you 2, for example. No nice number. There is no nice number that when we multiply it together 3 times gives us 2. If I do that on my calculator, sorry. I'm doing this for you right now. This is about 1.2599921, and again, it continues forever. So things like that. We have fourth roots, right? Fourth root of 10. What number times itself 4 times gives you 10, all right? So irrational numbers are a lot of not nice numbers. We don't like to see them come up, but they do exist, all right? So let me just flip this sheet over, and I'm just going to give you a string of numbers, and I'm going to say, tell me which ones are rational. So I'm going to give you a list here and you have to pick out which ones are. So 0, square root of 11, 2/3, 1.2, 3, 4, 5, 6, 7. 0.6298 repeating. And 3 pi. Okay, so of that set, which are rational numbers? So how about you turn off the video for just a second or pause it and then go through, and I want you to circle any numbers that are rational and X out numbers that are not rational or are irrational. Okay, so this contains a pi. Pi is irrational. 3 times an irrational number is just going to give you another irrational number. So this is not rational right here. There is no number, no rational number that we can multiply by an irrational to make it become rational. It just doesn't work. All right, 0, that is a rational number. It's actually a whole number. Whole number is the first set that it occurs in, and since whole number is contained in the rational, this is a rational number. Square root of 11 is irrational. Again, it's not the square root of a perfect square, so it's not rational. 2/3, this is written in the form a over b, where both of these numbers are integers and the denominator is not 0, so yes, that is a rational number. All right, this is not rational. It does not end and it doesn't repeat. All right, so again, it has a pattern, but that pattern is not repeating because it's just going to keep going on and on forever. So no. And this is a repeating decimal. So again, in our rationals, we could have either fractions, terminating decimals, or repeating decimals. This is repeating, so it is rational. All right, one more. Which numbers are whole numbers? All right, so let's go with 22/7, 11, -3, pi, 0, and square root of 4, and 0.3 repeating. Okay, so again, pause, circle any that are whole, cancel or cross out any that are not. Okay, so whole numbers, again, those are the natural numbers plus 0. So 22/7, no, that would not be a whole number. That's a fraction that doesn't simplify into a whole number. 11, yep, that's a whole number. All right, it's part of the naturals, and so it is also part of the wholes. -3, that's tempting because that looks a whole, but when we got the negative in front of it, that becomes an integer, and integers are the next set up outside whole numbers, so no. Pi, no, that's irrational, so it can't be whole. 0, yep, that would work. Square root of 4, that's tricky because, again, hopefully your mind is soon going to start making an association between square roots and irrational numbers, but you have to be careful because if this under here is a perfect square, then it is a whole number. So yes, that is, because this is just the same thing as 2. All right, 0.3 repeating. Again, if the question had been rational like it was up here, yes, that would be a rational number because this is 1/3, but 1/3 is not a whole number. All right, so no, that would not be it. All right, well, one last question. How would this change, if at all, if instead of whole, I said natural? Are there any that you would put back in? Are there any that you would take out? Okay, hopefully you realize that you wouldn't add anything back in. All these ones that are crossed out would still stay crossed out. But if this said natural instead of whole, this is no longer natural. So if I change that, that one would get crossed out, and the only two natural numbers would be 11 and square root of 4. Okay, that's it.